by Rick Muller. He's the Senior Manager for Advanced Microsystems Group at Sandia National Labs. And he's also the Deputy Director of the QSA, the other quantum institute that's funded through the DOE. Now, Rick is leading the silicon-based quantum computing effort at Sandia National Labs. So over to you, Rick.
Thank you very much, Umesh. And thanks to Dan for a great introduction to another center that is largely centered around Berkeley. I'm going to talk about a DOE-funded center called the Quantum Systems Accelerator that is led by Irfan Siddiqui at Lawrence Berkeley National Laboratories and in the physics department at University of California at Berkeley. And I'm the deputy director at Sandia. And so in addition to Sandia and Lawrence Berkeley National Laboratories, we have a really remarkable group of partners in the Quantum Systems Accelerator. And since Dan read his mission statement, I will read ours. The Quantum Systems Accelerator seeks to catalyze national leadership in quantum information science to co-design the algorithms, quantum devices, and engineering solutions needed to deliver certified quantum advantage in Department of Energy scientific applications. So again, like the CIQC, and unlike necessarily all of the other 5 DOE hubs in this area, we do focus on quantum computing. And a great partner to us in this endeavor is the Simons Institute. We use the expertise that the Simons Institute has, both to further our research goals and also for our workforce and ecosystem work, about which I will speak to in a few minutes. So the metaphor we used for how we are trying to identify and solve problems in the Quantum Systems Accelerator was this kind of picture that, often if you're hiking in the mountains, you don't know the path up the highest mountain until you're standing on the peaks of some of the foothills. And what the Quantum Systems Accelerator wants to do is stand on the smaller peak of noisy intermediate scale quantum devices and start to understand what the most fruitful pathways to take from those devices are to reach this mythical, it's not mythical, so to reach our ultimate goal of making fault tolerant quantum computing devices. So we try to identify what the biggest obstacles to progress in these areas are. And it will come as no surprise to this audience, but these are that quantum systems are imperfect and have limited coherence and fidelity. And so one of our goals is to develop optimized, noise-aware NISQ hardware. Additionally, it's challenging to control quantum systems. And when you can control quantum systems, those controls are often not extensible. And so another major effort for us is to develop high fidelity modular control techniques for these. And then the last two directly touch on work that is also explored by the Simons Institute. In general, we do not know the full domain of meaningful applications, certainly that NISQ hardware can use with a certified quantum advantage. And so we are exploring analog and digital quantum devices. We also lack the protocols to quantify and benchmark the hardware that we have. And so to understand when a computation is actually quantum supreme. And so again, the goal is to develop those techniques to identify quantum supremacy and to benchmark nascent quantum processors as they're developed. I apologize for the eye chart here. I wanted to give you an impression of the scope of the work that we're undertaking by the Quantum Systems Accelerator. We start in the bottom here with programmable quantum systems. So these are working quantum devices that we can start to put knobs on and understand how can we control them, how can we do quantum operations with them. We focus in our center on superconducting, trapped ion, and neutral atom qubits here. And obviously, we're also deeply concerned with the materials and the interfacial limits to the coherence in these devices as well. Now, on top of those programmable quantum systems, we want to build engineered systems that let us build prototype devices that let us explore the limits of these techniques. And so in our first phase, we are exploring extending the integration of superconducting quantum devices to 3D integration, exploring techniques to couple linear ion traps together to make 2D-like interconnected quantum processors there, and to explore the possibility of neutral atoms by making larger and more extensible neutral atom quantum emulators. And then at the end of the day, we want to be able to have noise-aware error mitigation, hardware and noise-aware compilation that can then ultimately help us understand how to benchmark these devices, and then what types of mathematical and physical simulations can we achieve with these devices. Okay, so we are already seeing science emerge from the Quantum Systems Accelerator that gives us great hope for the future of this endeavor. In the upper left, what we see is a recent publication in Science by John Bollinger and his co-workers in Boulder on using penning traps to make two-dimensional arrays of neutral atoms that can serve as quantum sensors for very fine-tuned electric field sensing with these penning traps. Similarly, out of the Lucan group at Harvard, we have a very recent Nature publication where the Lucan group has demonstrated the ability to first load imperfect arrays of neutral atoms, get up to 256 atom arrays, and then rearrange and repack those arrays and do computations on those arrays with relatively high fidelity that really pushes the limits to what we thought was possible in the near term with the neutral atom platform. And similarly, I wanted to cite something out of Umesh and Norm Yao and their co-workers. A recent publication in Physical Review B shows very promising performance by the rigorous renormalization group, first order phase transitions and topological phases. And this is compared to techniques that we've known have been useful for a long time, like the density matrix renormalization group. And in particular, this study shows much more robustness in sensitive areas in critical points in sensitive areas in these phase transitions that the rigorous renormalization group shows that the density matrix renormalization group does not show. Easy for me to say.
There's about 5 minutes remaining.
Thank you. So in addition to the technical goals, we have broad goals to enhance and nurture the quantum ecosystem. This involves developing a workforce for the quantum future, engaging with industrial research groups, and building a diverse and inclusive culture both within our center and in the broader quantum workforce. I'll just note here that the Simons Institute is a large part of our efforts in workforce development. Our goal is to use the expertise at the Simons Institute in hosting deep dives into technical topics in the theory of computation. And we're planning to host summer programs here, deeper research pods and other programs that will focus on and elucidate key QSA problem sets. And then finally, since this is an industry day, I wanted to say a word about our industrial collaborations. We have 3 levels of industrial engagement that we're looking at right now. The first are created-driven research partnerships, when we and an industrial partner can identify a key problem that we would like to pursue in collaboration. And so we've got a number of these with different industrial partners right now. In addition to this, we have a broader group of technology partners who don't have individual research problems that we're working on collaboratively, but whom we keep apprised of QSA research, and we meet with regularly to understand what their concerns and needs are for the quantum industry. And then as we develop intellectual property and other technologies within the QSA partners, it's our goal to understand how best to start new companies or otherwise share that technology with the broader area. So hopefully that gives you some idea of what the Quantum Systems Accelerator is doing. My email address is rmuller@sandia.gov. And if you're interested, please reach out to me and I will see that your questions meet the appropriate people there. So beyond that, thank you to Umesh and the Simons Institute for inviting me to give this talk, and thank you for your attention. Umesh, you may still be muted.
Hi, can you hear me?
Yes, we can.
Better.
Okay, great. Yeah. Okay, thanks, Rick. So I just wanted to say, if there are any questions at this point for either Dan or for Rick, there may be a minute or so for that, a minute or two, while we set up for the panel.
Dan, I have a question. Can you hear me?
Yeah, hey, Andre.
Just out of curiosity. So I think you mentioned, a lot of this workforce development programs that you are, that CIQC is kind of supporting, and they all are targeted at, undergrads, grads. Have you been thinking about high school students and getting them engaged in quantum computing?
Yeah, good question. So I'd say within our center, honestly, not so much. Across the entire QLCI landscape, there is sort of a lot of interest in this Q through 12 idea of bringing quantum education. I guess they must mean all the way down to kindergarten. I'm not really sure what it is we're going to teach them. Here's your toy. No, it isn't here. But no, that's not really been our specialization to this point. I don't know. That's a good enough answer. There's a lot of great efforts in this area that we can probably learn about, but we have to pick where we want to focus our attention, and that's not been where it is.
I will say, unsolicited, that in addition to undergraduates and graduates and postdocs, and although the QSA is also not focusing on high school students, we are experimenting with outreach to community colleges as ways of developing talent in people that may not be reached in traditional four-year universities.
Oh, Umesh, I think you're muted.
Hi, can you hear me now?
Yes.
We can.
Okay, sorry, I was just going to jump in for a moment and give, since Andrea has been working towards this goal of education for, I don't know, undergrads and high school students through something that you founded, QBraid. Do you want to say a word about it?
Oh, yeah, I guess it's mostly so far been with high school students, really. And I guess one program that we ran this summer, which was, I think, quite nice for the students, was we basically reached out to undergrads, across different universities who are already naturally interested in quantum. These are, undergrads that are involved in quantum computing clubs and that sort of thing. And we basically, got them to teach high school students in groups of, say, 20 or 30 students, a relatively small class for a period of, 8 to 10 weeks. And this was all free, and I think the high school students got a lot of it out of it.
Yeah, I will say, now that you mentioned it, that the QSA did a 2-week mentorship program through the JSTI that did connect high school students interested in quantum with quantum scientists at Lawrence Berkeley and at Sandia Labs, just to talk about, what your day is like if you are a quantum scientist. Not that there's any single answer to that, but just to kind of give them an idea of what kinds of preparation they'd need and what life is like in this area.
Yeah, because I think high school students nowadays are very precocious, and a lot of them want to, of course, not all people are interested in quantum, but I think given that quantum is right at this intersection between math, computer science, physics, it can be very stimulating.
Yeah, it's cool. Yes. Great. Thanks, Andrea, and thanks again, Dan and Rick, for really great talks. So now we can move on to the second panel. I'll introduce the